Well, looks like my plea for extra attendance worked out really well, doesn't it? Ha! They showed me. Okay, so we finished up a chapter on differential equations. Chapter 10, our last chapter in the book, is on Laplace transforms, which is a method for solving linear differential equations with inputs. So when we were looking at linear differential equations with initial conditions and no forcing terms, so x dot equals ax in state variable form, we found the matrix exponential was the key. And why that looks like a forbidding and foreboding computation to make, turns out that if you understand the eigenvalues and eigenvectors of the A matrix in the system, then everything just falls apart, because an eigenvector of A is also an eigenvector of the matrix exponential, and the eigenvalue gets transformed into the exponential of the eigenvalue. And that's cool because we understand what scalar exponentials do, especially when lambda is real. Positive value, it explodes, a negative value, it decays. When it's complex, we have to invoke Euler's formula, but it's not that much more complicated. And so if you're in the fortunate case when you have a basis for Rn built out of eigenvectors, then you can write the initial condition as a linear combination of eigenvectors. And to do that, you're just solving a simple matrix equation. You just stack the eigenvectors up as the column of a matrix, put all your coefficients into a vector, and you solve that linear equation. There's the B, here's the A, here's the X, AX equals B. And once you do that and you multiply the matrix exponential times your initial condition, you're back in this really nice expansion, because you apply each eigenvector in turn to the matrix exponential and you get the eigenvalues. And so once again, when lambda is real, it's very easy to understand. Lambda negative, we get decaying. When the eigenvalue is complex, it has a real part and an imaginary part. The imaginary part gives us the cosine and sine from Euler's formula. So this is where the oscillations come from. But the thing out front is decaying when the real part of the eigenvalue aj is negative. When it's 0, this is 1, so this just oscillates. And then when this is positive, it's exploding, and so you get exploding oscillations that increase. And it's not pretty when you see a robot arm doing that, so run and hide when that happens, okay? It's already a lot for you to be understanding what's happening with the exponential of a matrix and real eigenvalues and eigenvectors. So homework 8 will explore slowly and systematically what happens for the complex eigenvalues and eigenvectors. So today we're going to work on the Laplace transform. We won't get to feedback control until maybe second half of next week. But as a warm-up, I just wanted to look at a few simple properties of exponentials, and I want to allow the coefficients in my exponential to be complex numbers. So a real number A, a real number B, and then the I is square root of -1. And then I want to give you a preview of how the Laplace transform makes short work of differential equations, assuming you like algebra. And since I've told you several times that organic brains are not very good at algebra, you might think that's a poor trade-off going from differential equations to algebra. But in general, if you're careful and you've got good software by your side, it's all okay. Okay, so the first thing, and I posted these so you wouldn't bother trying to write them all down, but just want to make sure. Welcome. Let's make sure we can differentiate and anti-differentiate, in other words, integrate a complex exponential. So e to the zt, where z has a real part and an imaginary part. And this is just to help us get better and better and more comfortable with Euler's formula. So e to the zt then becomes e to the a plus ibt. This is a sum in the exponent, and we know our exponent rules, where we can write a sum as a product of the exponentials. And the first part is real, so that's straightforward. And then this is where Euler's formula comes in. So it's cosine of bt plus square root of -1 sine of bt. Now I claim when you differentiate that, you're going to get a z in front, just like we had e to the at, the a came down. And everything just follows the scalar case that we're used to with real numbers. So adding the complex number in here doesn't make it more complicated when we differentiate and integrate exponentials. But if you haven't seen it, it seems like it should be much more complicated. So let's just figure out how to differentiate e to the zt. And we'll do it by only differentiating real functions, things that we understand. So there's no cheating here. So here's e to the zt. We want to differentiate this. So by the product rule, it's the derivative of e to the at, which will be a e to the at, times this part. So we just copy that back down. Plus the first term times the derivative of the second term. And we know how to differentiate the real function cosine. We get minus sine. And then the chain rule, we need to bring a b out, okay? And we know how to differentiate the real function sine. We get cosine, and the chain rule brings a b out. So there's all of the terms. And then what we're going to do here is this -1, that's the same as I times I. And the reason that's convenient is because I've got an I here, and now I've got an I there, and I can factor it out. And so I see I have e to the at, I have b, and I have I. All of those things can be factored out. And then what's left after that, remember this minus sign is now plus I times I. I have cosine of bt plus I sine of bt, which is the original complex exponential. So I'm just putting things back together after breaking it all apart so I can differentiate using results I know for real functions. Putting it all back together, that's algebra. And so I get A e to the AT and A time, and I have IB times e to the AT, etc. So I break those out. I combine these back up. That's my e to the ZT, and there is Z. So there it is. By just simply grinding it out, the derivative of e to the ZT, when this is complex, changes nothing. It's just Z times the derivative. And from that, we know what the antiderivative is, because I put 1 over Z here. This thing is gone. And so I know the integral of e to the ZT, or its antiderivative, is 1 over the coefficient, just like we do with real numbers, plus a constant. So this is going to come up over and over while we're doing Laplace transforms that we need to differentiate and integrate a complex exponential. Questions on that part? Or seem straightforward, believable once you see it all, and then you never want to see it again. You just remember that you bring the coefficient down, right? That's what I did for 20 years until I started teaching EECS 216, and I remember, why is that true? Okay. We'll have some fun videos later. Okay, so once again, this is giving us an idea of the road we are going to follow. So it's sort of like mom and dad saying, hey, we're going to Disneyland and we're driving and we're going to go down through Ohio and then we're going to hit Virginia and then Georgia and Florida, et cetera. Okay, they're giving you a preview, even though you haven't seen Georgia and Florida and Virginia and Ohio. Let's pretend, okay? But you kind of know that they're states and they exist. So that's the same thing we're going to do here. We're going to have things in the time domain that are associated with differential equations. Some of them will be exponentials. And remember, sine and cosine, those are complex exponentials. So exponentials. We'll have terms from the ODE, y of t, its derivative. What the Laplace transform is going to do, it's going to take time domain functions and put them into what's called the S domain or the Laplace domain. And to signify that, we replace the lowercase things with uppercase y. That's just standard. We will compute the Laplace transform of exponentials, and it'll be really simple. It's a rational function, 1 over s plus a. The Laplace transform of derivative, it'll be s times the original Laplace transform minus the initial condition. I'm going to make things simple. Let the initial condition be 0. And what I want to show is that once we establish these types of relationships, solving a differential equation becomes pretty straightforward. If this is 0, y dot, it's just s times the Laplace transform of y. This is 3 times the Laplace transform of y. It's going to be an integral, and 3 times an integral is just the thing. And then here's our e to the AT, minus, plus, minus, plus. And so we've got this algebraic relationship that y satisfies. Well, we can do the algebra. That's s plus 3 times y, and then solve for y. So divide by s plus 3. And then we did partial fraction expansions very briefly, extremely briefly when we did antiderivatives. So we'll do a lot more of partial fraction expansions. But you've seen that products and more complicated rational functions, if you know the roots, you can break them down into sums of first-order terms. And here's the kicker. 1 over s plus 2. So if that's plus 2, then a is 2. This becomes e to the minus 2t. And this is plus 3. So a is 3. This becomes e to the minus 3t. And that's the solution of the ODE, and you're done. So it's magic, okay? It looks like magic right now. But it's kind of cool magic. So there's no matrix exponential. Yes. No eigenvalues and eigenvectors. I'll show you that the eigenvalues are hiding in there. But there's no eigenvectors. And everything is algorithmic. So I can write a piece of code that I just give it this, and then it produces this. Okay? So that's why we're going to do Laplace transforms. So the first thing we're going to do is define the Laplace transform and then compute it for a couple of functions. Get used to that. And then we'll start figuring out, well, if I know the Laplace transform of a variable, what is the Laplace transform of its derivative? And we'll build up and apply Laplace transforms to differential equations. And this magic will become ho-hum, boring, I got it. Shouldn't have taken that long for you to teach it, Professor Grizzle. It was really easy. That's my goal. Are we excited? Online, are we excited? Yes, we are so excited because we're doing differential equations, and that's the reason most of us are in this course this semester. Okay, so let's just get started. We'll say a function takes real numbers to real numbers, is right-sided. When f of t equals 0 for t less than 0. So what's the intuition here? On the left side of the origin, the function is 0. So it only takes interesting values on the right side. That's why we're calling it a right-sided function. You could do the opposite and have a left-sided function, and you could take every function and write it as the sum of the two. We don't need to do that. So we're going to take functions that start at t equals 0. That's another way to say it. So this is just our technical background. And then this one is, let's recall piecewise continuity. Draw the picture, then I'll write down the techniques, and you guys will go, oh yeah, I remember that. So I'm going to draw the function to be right-sided. Oops, it doesn't need to be there, but it could. Etc. So this is a point of discontinuity, okay? And so the idea of piecewise continuous is that for any bounded interval AB, f of t, I guess it'd be easier if I labeled f, has at most a finite number of discontinuities and then at those points of discontinuity, the limits from the left and right both exist and are finite. Okay, both exist and are finite. So anything that's blowing up like 1 over t or something at the origin, that doesn't work. Why do we care about this? Well, we know how to define Riemann integrals for continuous functions, and since we can break up the Riemann integral from 0 to something as we integrate to the first point of discontinuity, then we go from the first one to the second one, etc. As long as on any bounded intervals we have a finite number of integrals to add up, everything is cool. And so this definition of finite continuity makes sure that all piecewise continuous functions are Riemann integrable. So that's the only technical thing we're just recalling. It's so that the Riemann integral exists. Okay, and then examples. Whoops, you're supposed to have switched. So I'm drawing it in a way that it's not really a function, right? But that's a square wave. So that's piecewise continuous, it's periodic. Piecewise continuous. And then if we were to do something like this, so I just take tangent and then make the function 0 at multiples of pi over 2, so I let the function be 0, t equals pi over 2k, k equals plus 1, 3, 5, 7, okay, and then tangent of t otherwise. Not piecewise continuous. So this function has on any bounded interval a finite number of discontinuities, but the limits from the left and right are not finite at the points of discontinuity. They're unbounded, so it's not piecewise continuous. Okay, so it's just reminding us of what we need to do Riemann integrals. Okay, so let's define the Laplace transform. So for a right-sided piecewise continuous function, the Laplace transform is typically write it with a script L. So that's kind of cool. Laplace of f of t is by definition equal to. This is 0 minus, so that's a limit. This is infinity. That's another limit. It's the integral of f of t e to the minus st dt. Where s equals, let me catch up. That's called the Laplace variable. Okay, so where things get a little bit sticky when you're first learning this is 0 minus, really? Right-sided functions? Right-sided functions are 0 for all t less than 0. So limit from 0 minus, that should be 0. We shouldn't have to worry about 0 minus or 0, okay? So that's the confusing part in the beginning. Okay, so just warning equals heads up. Zero minus only shows up for initial conditions. Okay, so it's like everything. Once you've done it a few times, it seems very natural. But in the beginning, and so we will pause and emphasize it, and you'll think that I'm overdoing it, but that's okay because it'll help you remember and all that kind of stuff. Okay, so this is an improper integral, and it involves, in theory, a lower limit, and then this is definitely an upper limit that we have to calculate in a hard way. So let's compute our first Laplace transform. Okay, we'll take the function f of t is the unit step function, and I'll remind you of its definition. Unit step of t is 1 for t bigger than or equal to 0, 0, t less than 0. You know, I could graph it, but it's just a 1, okay? So that part we can imagine, I think. So it's right-sided and piecewise continuous, so everything is cool. So if we put that puppy under an integral, we're not afraid of it. So let's get to work. So Laplace, unit step of t is by definition equal to this crazy improper integral. Okay, so why are we doing this one first? Well, because if this is a 1, all we have to deal with is finding an antiderivative of this exponential term, and we know how to do that. We just did that. We did e to the zt. So we take z equals minus s. We know how to integrate that. So that's why we're doing something super simple here, because we know how to do an antiderivative there, and that'll help us evaluate this integral, okay? So 0 minus infinity. If you'll forgive me for not putting a 1 dot, just assuming you guys get it, that there's a 1 there, or maybe I can just put it there. Okay, so we want to do the integral. We do the derivative of the exponential, the antiderivative of the exponential, and we evaluate 0 to infinity. Okay, can we handle it? So I'm going to put the minus 1 over s here. And then this is limit t goes to infinity of e to the minus st. Right, so I got rid of that minus sign and the 1 over s, and I'm focusing on this part now. And I'm writing it out as, yep, I have to do the limit, okay? And then the second thing is minus limit t goes to 0 minus e to the minus st. Okay, no cheating. No cheating here. This limit is easy because this function e to the minus st is continuous. So the limit is just e to the minus st evaluated at t equals 0 minus, and that's equal to 1. Okay, so put 0 in there, I get 1. From the left, from the right, top, center, bottom up, doesn't matter what the limit is, the function's continuous. This one is a little bit more challenging. So let's break that one out. And then, once we've done this kind of limit for twice, we're going to go, got it! I don't have to do that again, okay? t to infinity, e to the minus st. Limit, t goes to infinity, minus sigma plus I omega t. That's the Laplace variable. It has a real part and an imaginary part. Oh, where's my exponential? E. Okay. I'm getting too excited that I'm leaving out things now. So e to the minus sigma t, e to the minus I omega t. And once we've written something like this out a few times, we kind of quit too. So this becomes cosine of minus omega t, which is just cosine omega t, but I don't care. And this is plus I sine of omega t. Once again, I'm just blindly plugging into Euler's formula. And if you want to use trig identities to simplify the cosine and the sine, using that cosine is even and sine is odd, more power to you. Okay, so this limit is equal to what? Well, sigma is, positive, so minus sigma is negative. So we have e to a negative number times t as t goes to infinity. That goes to 0. And then otherwise, so sigma is 0 or positive. Sigma 0, that's just 1. But when t goes to infinity, these things don't have limits. And then if sigma is negative, this term explodes, and this still doesn't converge. Okay? So the limit is simply undefined. So let's see if we agree with this. So this is the strange thing that happens when we do Laplace transform, is that it's not defined for all possible values of s when we look at the integral. Okay, so we wrote down the definition, which seems mysterious because we didn't do Fourier series and Fourier transforms and understand the history of how Laplace knew what Fourier was doing, and he then extended Fourier's work. We just got a definition. Sad for us. But we do the integral, and doing the upper limit of the integral, we have to evaluate this limit. And this never converges to a limit, so it's only way it's going to have a limit is when this thing decays to 0, and then the limit is 0. Otherwise, it's undefined. Okay. I want to make a minus sign mistake here. Yes. The Laplace transform of the unit step of t equals minus 1 over s times the first limit, 0, minus the second limit, 1, and that's when sigma equals real part of s is positive, and it's undefined otherwise. So if the real part is 0 or the real part is negative, it's undefined. So we're being super careful, super fussy, and pretty soon we will stop being that. But a minus times a minus is a plus. So that's 1 over s, real part of s positive, undefined, otherwise. And we write this in a much more convenient form, because having these cases, that's really awkward. We write this as Laplace of this transform of this function equals 1 over s with this is the complex numbers. Okay, and ROC stands for region of convergence. Okay, so the Laplace transform of a function that's 0 and then 1 is just 1 over s. The Laplace transform is an improper integral, and this integral doesn't converge for all values of s. When this is a constant 1, it only converges when the real part of s is positive, so that this is a decaying exponential times some oscillating terms. So the region of convergence is all the values of s where this integral makes sense. So that's what region of convergence is. Now, turns out when we're dealing with the Laplace transform, we can forget about this region of convergence. You have to play with it in order to see that. So don't get your shorts tied up in a knot, if I'm allowed to use that low-class vocabulary, about the region of convergence. The main thing to have in your mind is that there's an association of a time domain function and a function of S, and that's the algebra. Okay? We'll carry this around for today, but after that, we won't do it anymore. Okay, I want to show you what a table of Laplace transforms looks like. Fit on the page? Oh, it does. Then some. Okay. This list is all the Laplace transforms that us engineers ever use. There's just a few of them. And in fact, they're almost all the same. And they don't look the same right now. We won't use this impulse function. But there's the unit step. And so in theory, we should have the time domain function, its Laplace transform, and then the region on which the Laplace transform is defined. But once we've done a few, we'll be able to look at this and go, yeah, that's it. And because this is s to the n plus 1, it's still just that. Whatever s is in the denominator, the real part of that has to be positive. So all of that's a mystery right now. Oh, come on. Go back. All of that's a mystery right now, but it'll work for us in a little while. I'll clean those up later. So let's compute another couple of these. And then we'll just say, if we need a Laplace transform, we simply look it up, because nobody ever computes these things by hand. Okay? You should know how to compute them, but you never compute them by hand. Questions so far? Just tedious integrals and tedious limits to evaluate. It's not hard, but to be careful is a little bit tedious. Okay. So even when I was an undergraduate, after doing a few of these by hand, we got to use the tables too, okay? So you guys get to do that. Okay, let's take another function and make it e to the at times unit step of t. Now, the reason we multiply our functions by the unit step is that automatically makes it right-sided. And then since the unit step is piecewise continuous and the exponential is continuous, this whole thing is piecewise continuous. So it's all good. All the integrals we write down, they make sense as long as we just check the limits, because they're improper integrals. So Laplace, e to the at unit step of t. Well, you know me, I like us to write down the definition a couple of times until it becomes repetitive. That's how we memorize things. We put the function, then we put the magic sauce from Laplace, the e to the minus st dt. We have a product of exponentials. The natural thing is to add the exponents. So we continue the limits for the moment, and we just do algebra. And I'm going to write it like this. So if you had left it as a minus s times t, it makes no difference. It's the same function, okay? It's the exact same function. Now, having the minus sign out front makes it look just like the previous integral we did with e to the minus st, okay? Except s is replaced by something else, but it's still trivial to do the antiderivative. So it's minus 1 over s minus a. Okay, minus quantity s minus a, that's z, so it's 1 over z. E to the minus s minus at. And then we've got these limits. Okay, so going to be two cases. Real part of s minus a is positive. You guys do the limits for me. When this thing is positive, when I put infinity here because of the minus sign, I get what? Is it this or is it this? Okay, they're the same thing because we love 0, okay? It makes things nice, okay? So that's going to be 0. Where are we going to get a contribution from then? Well, when we plug in the lower limit, and we plug in the lower limit here, because this thing is continuous, we just get 0, we get 1 here. And so the lower limit has this minus, it cancels that, and we get the same thing as we had before. Okay, whatever the exponential was, we get that. And it's undefined otherwise. So in other words, when the real part of s minus a is 0 or negative, when we plug in infinity, this just doesn't make sense. It doesn't converge. The limit doesn't exist. Okay, and so we write this as equals 1 over s minus a for region of convergence equals real part s minus a positive. And note, we use the same limit analysis. As we did for e to the minus st. Okay, so we don't care what the imaginary part is, that's oscillating. It's the real part. Is it crushing down or not? And if it's not, there's no limit. And if it's crushing down, the limit is 0. So that's what makes all of these things simplify to these simple answers. Okay, so this is the hard work, figuring out what that limit is. But they always work out to something simple. And then after a while, you just write it down and you don't do the limit analysis anymore. Okay, we're past the 5:20 point, so we should take our break, okay? And let your brains chill a little bit, then we'll come back. And we'll come back and we'll do another one, get some consequences of this, and start applying it to a differential equation. That'll be more interesting. Okay, so the Laplace transform of a unit step is just 1 over s. That's very easy. And the Laplace transform of e to the at times a unit step is 1 over s minus a. And we use the limit analysis to arrive at that. So let's just note. When a is real, the real part of s minus a is the real part of s minus the real part of a, which is just the real part of s minus a. And the only reason I'm writing that down is because that means then that the real part of s minus a is positive if and only if the real part of s is bigger than a. So that's another way to write it down. Now let's suppose this number a is purely imaginary. So it's I times omega naught, where omega naught is some real thing. Then the real part of s minus a, so real part of s, real part of a. Well, it's just the real part of s, because the real part here is 0. Okay, there is no real part. And then we get that the real part s minus a is positive if and only if real part of s is positive. You're going to say, okay, yeah, we're down in the weeds. I know. So let's ask the question, why do we care? Okay. And yes, it's beautiful math and all that kind of stuff, but Euler's formula tells us that cosine is e to the I omega naught t plus e to the minus I omega naught t over 2. Okay, so that's Euler. So if I take the Laplace transform of cosine omega naught t, what do I get? Well, I should say cosine omega naught t times the unit step of t. Never leave it out. Okay, so it's 1/2 Laplace transform e to the I omega naught t unit step of t plus 1/2 Laplace transform e to the minus I omega naught t unit step of t. So just use Euler. It's an integral, so the integral of a sum is the sum of the integrals, and bring the half out and all that kind of stuff, okay? And what do we get? Well, this becomes 1 over s minus a, s minus I omega naught. And it has region of convergence, real part of S positive. Whoops, I left out my half. Plus a half. And this Laplace transform is 1 over S minus A, so that becomes S plus I omega naught. And it has the same region of convergence. So we can just add these two things up. So we get a half here, put everything over a common denominator. Right, so we multiply top and bottom here by this one, and here we multiply top and bottom by this one. This cancels with this. So we get 1/2 2s. Anybody see what we get in the bottom here? It's an a minus b times a plus b. So I did the a squared minus I times I, that becomes plus 1, and omega naught squared. Oops. Not omega to the 0, Grizzle. It's omega naught squared. Then once again, region of convergence. So what did we do? We avoided integrating cosine against sine by replacing it with Euler's formula. And you can do every single one of these. So every single one of these, exponential, here's another exponential, right? We just combine them and we do it, and then when we combine them, this is what we get. We get an s minus a, just like we had unit step, we got a 1 over s, e to the at unit step, s minus a. Here, we did cosine, we get s minus a. So it just shows up in a very simple way. And so we're not going to calculate any more of these because they're almost the exact same integrals as we've done before. And with the t's here, you have to do one integration by parts. It's tedious, but not enlightening. So that's our table of Laplace transforms. So they're all just tedious integrals. And all of these things called region of convergence, they just follow from when that integral is well defined. Nothing more, nothing less. Questions about that? It's almost anticlimactic, okay? You've got this really fancy thing, and it turns out, wow, It's really easy to evaluate for most functions of interest to engineers. Okay, so now that we know how to compute Laplace transforms of functions, how do we use it to solve ODEs? Okay, so for that, we need one more result, and then we'll have all of the tools needed. So Devin, you'll have to tell me if what we've covered and what we're going to do is going to be everything you need in EECS 215 for using Laplace transforms. I'm guessing it is, okay? And it's probably more detail on why the integrals exist and all this stuff about region of convergence than I would do in EECS 215 anyway. EECS 216, that's where we do everything. So the proposition says the following. Suppose that f of t is differentiable, right? Those are the kind of functions that show up in differential equations. They're differentiable. Yep. That sounds like something to do with ODEs. So suppose the function is differentiable. And that both f of t and its derivative have Laplace transforms. Okay. Then, this is the crucial piece. The Laplace transform of f prime of t is s times the Laplace transform of f of t minus f of 0 minus. Okay, small little remark. This is just notation. We often write f of s for the Laplace transform of a function. Okay. So what this also says is that the Laplace transform of f of t is s times f of s. Okay, so there's capital F of S, there's the S, and then F at this mysterious 0 minus. It's still mysterious for us, but that's okay. Now, I'm going to show you a little bit about the Y, but we're going to do not quite everything on it. It's true because of integration by parts. And once you see why it's true, I'm not going to do every detail. But it's not a mystery. It's something that you can just grind out. integration by parts. I didn't see that coming. Well, no, you did. You did. Here's the Laplace transform we're talking about. So there's an obvious dv, and there's an obvious u. So remember, this is uv from 0 minus to infinity, minus the integral of v du. If dv is f prime of t dt, that implies v is just f of t. If u equals e to the minus st, du is, the coefficient comes down, okay, so all we do is just plug those in, and then we've got a gnarly limit that I'll wave my hands about because it's done carefully in the book. Okay, so this is u e to the minus st times v, which is f of t, minus v is f of t, and du, I'm going to emphasize the s. So the minus s comes out with a minus sign, so this is just s, Laplace transform of f of t. Okay, so that's where the s, f of s comes from. And this is delicate. But when you do it carefully and you put s where it's in the region of convergence of both the Laplace transform of f and its derivative, this term equals, this is minus f of 0 minus. And so you get s. Okay, so the arguments are similar to when we were plugging in the t and taking the limit as t goes to infinity. This is never a problem. It's always this thing. And so the only way that this thing gives something without oscillations is when this is, the exponential is able to crush everything in the function, and you need to be really careful when you do that limit. But that's what you get. So the key thing is it's really integration by parts. In the integration by parts formula, the du gives you the s e to the minus st, and then the minus and the minus makes a plus. So, okay, s is differentiation. And yes, 1 over s That is integration. So S differentiates. When you invert that, you integrate. But that's how you cancel in algebra something. You multiply by its reciprocal and you get 1. And so that's how d by dt and integration match up. It's kind of cool. Really cool, actually. Okay, so this is the second table that all engineers know. Okay, so the first line is the one that we derived. Let's just check the second line, and then you'll see that all of them are just f double prime of t. Okay. So let me write this in a way that I can apply our previous result. Okay, so the second derivative is the derivative of the first derivative. So the Laplace transform of a derivative, so this is equal to S times the Laplace transform of f prime of t minus f prime of 0 minus. Okay, so I just put f prime for f. And then this is s f of s minus f at 0 prime. And you multiply these out. In the second derivative, you get an s squared. Surprise, surprise. And then we'll see that these are how initial conditions of ODE show up. Okay, so you don't have to do integration by parts 4 times, 5 times. You just recursively say the nth derivative, or n plus first derivative, is the derivative of the nth derivative, and then you do it by induction. So they all look like this. S, where f of s is the Laplace transform of the function, then you get s squared. And these are hard to memorize at first. So the only thing I memorize is this one. And then when I can't remember whether it's S goes here or it's S, F prime, and the F here, I do this substitution, okay? So that's just how I work. What you'll do is you write it on your cheat sheet for the final exam and you'll be fine, okay? So you'll have it on your cheat sheet. But when you're sitting there and you're working things with a friend and you're showing them how, and you know, my memory's not perfect. The reason I like math is because I can derive 27 things from just 2 facts, okay? And so I get this formula easy, and then I see the pattern. It's always the highest derivative times the function, and then a less 1 times that, etc. So there's a pattern to it. So. Superpower of Laplace ODEs become algebraic equations. Let's see how that works out. Okay. So let's solve our first ODE correctly instead of just me saying, hey, you do this substitution and that substitution, and then it's just algebra. So solve. So we're going to make the ODE super hard. It's first order. Y dot of t plus 3y of t equals e to the minus 3t unit step of t. And we're going to have an initial condition of 4. Now, this is where I need to tell a little story. So when we're looking at our inputs, these things, so these are signals that typically we, the engineer, are applying to the differential equation. So it's us sending a motor command. It's us driving the car autonomously and reading the street lights. So the street lights are green until they're red. When they're red, there's no past, okay? They just switch instantaneously from green to red, instantaneously. When I send a speed command to my Segway or Ballbot, or I send a torque command to the motor, it can change as fast as my electronics works. However, states of a differential equation, suppose Y is the current through a resistor and a capacitor. That current, in theory, exists for all time. I built this device, it has a past. What I'm doing here is setting the time that I start observing it. So at that time, the current is 4 amps. Or if it's a mass and a spring, I've got a position and a velocity on this system. So I have initial position and initial speed. Where did they come from? They came from Grizzle compressing the mass in the spring or whatever, or you applying a voltage to the RC circuit. Okay, so it has a past. We may not know who was providing the inputs, but we can just instantaneously with our instruments measure the current, and we call that initial time and initial value. So states of the differential equation are what these things apply to. When we're doing signals, they have no past before t equals 0. They're just functions of time, and there is no value at t equals 0 to subtract. And that's good because the unit step, is it 0 at t equals 0 or is it 1? Well, that's kind of arbitrary. And this e to the at, is it 1 or 0 at t equals 0? I don't want to decide. So that's the story, and I'm sticking to it. So the red flag or danger Will Robinson that we'll talk about is that you use these formulas for the left-hand side of a differential equation. So if I now define, Laplace transform of y of t is y of s, the Laplace transform of y dot of t is s times y of s minus y at 0 minus equals s y of s minus 4. Okay, so it's left-hand sides of differential equations have a past. That state existed before we decided what the initial time was. That's the initial value, where signals, they're all 0 before our initial time. They're all 0. That's the confusing thing to keep track of. Now, from our table, anybody remember what it's equal to, the Laplace transform? E to the minus AT unit step has Laplace transform 1 over S plus A. So this is 1 over S plus 3 from our table. Okay, so when we do the Laplace transform of our differential equation, this is the cool part. Laplace transform of y dot. Whoops, I don't want to do everything in red. So we have the s y of s minus 4. Then we have 3 times y of s. And then we have the equals 1 over s plus 3. I'm going to solve for y of s. This is algebra. So we end up with s plus 3 times y of s plus 4 equals 1 over s plus 3. Whoops, s plus. Oh, yeah, that's correct, s plus 3. Thought I made a mistake, but I was wrong. How about that? And this is, I did make a mistake, that's minus 4. Okay, so now I'm going to get y of s on one side. Well, the easiest way to do that, I've got my 1 over s plus 3. I move the 4, and this is a 4. And then I divide everything by 1 over s plus 3. So that's just algebra. And notice I made a mistake right off the bat where I got my minus sign wrong, okay? So humans are really bad at this. Let's see, this is s plus 3 squared, and this is 4 over s plus 3. So now y of t is the inverse Laplace transform of y of s, which is the inverse Laplace transform of 1 over s plus 3 squared, plus 4 times the inverse Laplace transform of 1 over s plus 3. Okay, so y of t is the inverse Laplace transform of y of s, which is the Laplace transform of y. So inverse applied to that, yeah. So what is it? Well, that's where these tables are handy. So one of our things is the inverse Laplace transform of 1 over s plus 3. So s plus 3 means a is minus 3, and so we get e to the minus 3t times the unit step. That's s plus 3. A is minus 3 for that to work, so a is minus 3. The next one, we have n equals 1, because we have a square. 1 plus 1 is 2. We have s plus 3, so once again, a is minus 3. N is 1. 1 factorial is 1. T to the n is t. A is minus 3, so we just plug it in, and we get t e to the minus 3t times unit step. We just use the table. It's brain dead, meaning it's full of places to make errors, because if it's brain dead, we don't pay much attention, right? Okay. So using our tables, so this one is t e to the minus 3t unit step of t, and that's 4 e to the minus 3 unit step of t, and this is from our tables. Or table, actually. You impressed?
Flustered.
Excuse me?
I'm a little flustered.
Flustered. Wow. That's a good state to be in so that learning can take place, okay? If you're not a little bit frustrated, then you don't try. Okay, so you want to talk it out? Where's the frustration?
It makes sense. It's just like a lot at once, but like it all makes sense.
Yeah. So let's. So we've got this magical thing called the Laplace transform, which allows us to handle terms like this. Here we had the initial condition be 0, so this is just s times capital Y of s. This is 3 times y of s. And since this is t greater than 0, the unit step is implied, and e to the minus at goes 1 over s plus a. It's algebra. We solve for this. That's a product. Here, we use this trick from when we were doing antiderivatives of rational functions. We write it as a sum of first-order terms. And then from our table, e to the minus 2t and e to the minus 3t. And then the unit step is implied because I've got t bigger than 0. Does that make it seem smaller and more contained when you go back to that? Yeah, but here we were just doing stuff without understanding that there is a pairing between time domain functions and functions of s. And that pairing is just tedious integration. It's just tedious integration and careful limits. This is where the magic happens when you relate the Laplace transform of the derivative of a function to the Laplace transform of the original function. And y double dot is s squared y of s minus sy at 0 minus y dot at 0 minus, and then you can do y triple dot, quadruple dot, etc. And so all the derivatives disappear and they're replaced by algebraic functions of s. That's the magic of Laplace. Intrigued at least enough to dig through a couple examples? Where'd I go? Too far? Yeah. Okay, suppose you wanted to check that this was actually the solution of the differential equation. Well, plug in t equals 0, this goes away, and you get 4. That's cool. Okay, and then differentiate this. I don't want to do it for you, but you've got to apply the product rule here and stuff, and then just plug everything back into the differential equation and see that it works. Tedious, okay, but very doable, very doable. Okay, so we'll get more practice on this on Monday. Let me just close with a fun video. And it's fun for me because it goes back to something from my childhood. You're going like, okay, so let me start with this, which is nobody's childhood. It's just all of us growing up.
Yesterday you likely saw them, so yellow flags mean that.
Let me see if I can get the volume up.
There's a medium hazard with moderate surf and or currents. Weak swimmers are discouraged to swim. Red flags, got to talk about that instead. A red flag warning means only strong swimmers should enter the water, and double red flags mean the water is just too dangerous and no one should swim.
So in common parlance, you guys in your text messages or whatever, you say red flag when you mean danger, warning, whatever. Correct? Not correct? Correct. You may or may not have recalled that it comes from flags at initially Bondi Beach and then all the beaches in the world, right? Yellow flag, meaning, it's a little bit dangerous out there. Red flag, maybe we saw some sharks, the waves are 2 meters high, there's undertow, only the top swimmers in the world should be out there. Okay, so that's what red flag means. Now, this is the fun part, okay? Because it dates me.
Danger, Will Robinson. Danger. Danger, danger, Bart Simpson.
Danger, Will Robinson!
Pour me a slice, Will Robinson! Danger! Danger!
Danger, Will Robinson. Danger.
Danger! Danger, Will Robinson!
Danger! Danger, Will Robinson!
Danger!
We'll keep going. So that's the original robot, and you know what the name of the robot was? Robot. Very original. So don't get stumped next time they ask you, what was the name of the robot in Lost in Space? It's a trick question. It's robot, okay? Now, so they didn't have a great imagination of what robots should be. That thing at the top is this positronic brain from the sci-fi novels of the 1960s and 50s, okay? What is a positronic brain? Well, we haven't created one yet, so we don't know. But one day, you know, maybe it's a fancy neural network, okay? So this robot... This robot was assigned to guard the little boy Will when the family Robinson was flying through space. And whenever something dangerous would come into the scene, it would start waving its arms around and going, danger, Will Robinson, danger. Okay, so we use in this my textbook in this course, danger, Will Robinson to mean red flag. And we use danger, Will Robinson because there's a robot involved whose name is Robot, okay? And that's much more fun than red flag. Do we agree on that at least? Okay, maybe we're not equally in agreement of how awesome Laplace transforms are because we haven't had enough practice with it, and we'll get more on Wednesday. But we're happy with now when you see in the book, danger, Will Robinson, that just means red flag warning. And you've made a cultural connection with your professor. Is that good? Of course it is. We'll stop here. Thank you, everybody. Hope you've had fun and keep learning. Oh, Kane has a CS roommate.